Welcome to my presentation with the topic Combining Metaheuristics and Process Mining to Improve Cobot Placement in a Combined Cobot Assignment and Job Shop Shadowing Problem. My name is Alexander Kinast and I work on this topic with my two supervisors, Karl Dörner and Stephanie Rendelemar. Let us head over to the agenda. Okay, let us start with the agenda. In the first part of the presentation, I will explain some important terms, including job shop shadowing problem, cobots, genetic algorithms, and process mining. After this introduction, I will explain a problem that we are facing and a solution that we have developed. The fourth topic will be the results that we could achieve with our developed method. In the end, I will give a short outlook about our plans to combine metaheuristics and process mining. Let us start with the introduction. In a simple job shop shadowing problem, jobs, tasks, and machines are given. Jobs group together tasks logically. This can be seen at the top of the picture. An example job would be the production of a motor. To produce a motor, many logical tasks must be done. For the tasks we already know a deterministic production time. Optionally, tasks can have precedence relations. This means some tasks can only start once preceding tasks are finished. In a simple version, tasks can be produced on all workstations, and an available time for all workstations exists. This can be seen in the center of the picture. The optimization goal for such a job shop shadowing problem could now be to minimize the makespan. The makespan is the time until all tasks have been finished. This can be seen at the bottom of the picture. Let us head over to an explanation of cooperative robots. Cooperative robots have the abbreviation cobots. The difference to fully automatic industrial robots is that cobots can share a workspace with a human actor and no safety distance is necessary. On the top of the picture, a typical cooperative workstation can be seen. There the human worker places screws on a mechanical part and the cobot screws them in. Therefore, three production options exist. Humans can do all the work on their own. Cobots can do work either on their own or in cooperation with humans. Typically, industrial robots are used if the work allows a high degree of automation. Cobots can then be used on workstations where 20 to 40% of the work can be automated. It is assumed that the cobot increases the speed of a workstation by around 30%. On the bottom of the picture, a real-world production workspace can be seen. This picture is from the car manufacturer BMW from the location in Dingolving. Okay, let us head over to how we can use genetic algorithms to assign cobots to workstations. I will start with an overview about a genetic algorithm. The job shop shadowing problem is an NP-hard problem. This means that large instances cannot be solved exact in reasonable time. Different metaheuristics, such as genetic algorithms, have been applied successfully on job shop shadowing problems to find nearly optimal solutions in reasonable time. A genetic algorithm is inspired by natural reproduction and has the following steps. First, a population is initialized with random solutions. The next step is a fitness assignment, where fitness value is assigned to each individual in the population. With a fitness value assigned, the parents for the next generation are selected. In the crossover step, new children are created out of the selected parents. After creating new children, they are mutated with a given probability. The mutation is used to reintroduce genetic information if important genetic information has been lost. A fitness is assigned to each individual in a new generation. If a stopping criterion, like a target fitness, a maximum generation amount, or a given runtime has been reached, the algorithm will stop. Otherwise, the algorithm will continue with the next cycle, with the parent selection. Okay, let us head over to the second part about genetic algorithms. To use a genetic algorithm for a job shop shadowing problem with cobot to workstation assignment, a special encoding that can handle the cobot to workstation assignment is needed. Last year at the ISM, we presented a biased random key encoding that takes tasks, relations, workstations, and cobots as input. Based on this input, a solution tells you which task is produced in which order on which machine, and which machine is supported by a cobot. Okay, let us head over to the basics about process mining. Process mining is used in three major categories. The first category is process discovery, which focuses on the discovery of a process model out of a process event log. The second category is conformance checking. The goal of conformance checking is to compare an event log with a given process model and find out how well it conforms to the original model. The third category is process enhancement. Also in this category, the process model is given. Based on an event log file, the original process model should be enhanced. The focus of this presentation will be on process discovery for event logs where no process model is given. I will now give a short introduction into the problem. The problem that we try to solve is similar to the basic job shop scheduling problem that I described before. Tasks are grouped as orders and can have preceding tasks. Similar workstations are grouped and tasks can be done on all workstations of such a group. Each workstation has a speed and a cost factor that change how fast a task can be produced on this machine and how much the production costs. A fixed amount of cobot should now be assigned to the workstations to improve the production. I will now go into more detail in the objective function. To optimize a job shop scheduling problem, multiple objective functions can be used. Examples for these objective functions are to minimize the production cost or to minimize the make span. A simple but commonly used objective function is to sum up the production costs and the make span. This is the objective function that we used in our paper. With this objective function in mind, the following questions come up. What factors influence the cobot to workstation assignment? Can process mining visualize relevant factors that led to the decisions of the genetic algorithm? And can information gained from the process mining improve the quality of the results found by the genetic algorithm? Based on these questions, we developed multiple scenarios that demonstrate basic concepts of process models. These scenarios have been solved by the genetic algorithm, and the event log file of the best solution has been created. Process discovery should now be used to visualize the implicit knowledge that has been created by the genetic algorithm. Explorative analysis on these process models is used to generate knowledge about which factors are relevant for the placement of a cobot. I will now explain how the process mining steps work in detail. On the left side of the picture, we can see how an event log file looks like. At the top of the file, extensions are imported. These extensions define which properties can be logged to the file. Examples for these extensions are a date and time extension, a lifecycle information extension, or extension that is used for organizational information. Based on these properties, a specific set of process mining algorithms can be applied. The main part of the file consists out of traces and events. In our example, a trace is used for an order and one event is used for a task. On the right side, we can see a mined BPMN model that is enhanced with additional information. I will explain this on the next slide. A process mining algorithm, the inductive miner, is used to mine a process model out of the process event log. This event log is converted to a BPMN model and enhanced with additional information. All nodes represent a workstation in the production, and each node is colored based on the created costs. Red workstations have high costs compared to other workstations, and green workstations have low costs. The width of each node is changed based on the total production time of all tasks in this workstation. The width of the node increases if the node has a high production time. The created models have been analyzed, and the following properties are relevant for the cobot placement. Some of them are pretty obvious, such as the total production time and cost in a specific workstation. However, it might not be obvious that the duration of individual tasks, the number of tasks, workstation groups, or the general scenario layout have an impact on the cobot placement. I will now head over to an outlook of our planned work. In our upcoming work, we want to focus on two major topics. The first topic is how we can improve process mining as a process visualization tool for metaheuristics. The second topic will be the automatic knowledge generation with process mining during the run of a metaHeuristic. This automatic knowledge generation should be used in the metaHeuristic to improve its performance. Thank you for your attention.